Hi everyone, welcome to KULTREP. So in this session, let us discuss analysis of the buck converter, boost converter and buck boost converter. Now, to analyze the buck converter, boost converter and buck boost converter, so we need to take some assumptions. Let me discuss that assumptions now. So here, what are all the assumptions are there? So let me write the assumptions here. Let me write the assumptions. The first assumption is all the components that are used in the converters are ideal. So what are all the components that we are using in the converters? Switches, right? Inductor, capacitors. These are all the elements we are using. We are assuming that switches and inductor and capacitor are assumed as ideal. So components are assumed as, all components are assumed as ideal. All components are assumed as ideal. Let us discuss the second assumption. So let us assume that the switch turn on time is the switch turn on time T on is assumed as D into T. The on time of the switch is assumed as the D into T. The turn off time of the switch is assumed as D dash into T, which is equal to 1 minus D into T. 1 minus D into T, where D is the duty cycle, so which is equal to T on by T, where D is the duty cycle, which is equal to T on by T. And if you add these two are D plus D dash, which is equal to 1. So what is the second assumption? So the turn on time is assumed as dt and turn off time is assumed as d dash t. So if we add both of the turn on and turn off of d plus d dash, which is equal to 1. So now let us see the third assumption. These all three converters are operating under steady state. So three converters are operating under steady state. Operating under steady state. What does it mean? Let us see. For example, let me take an example of the buck converter. So how the buck converter can be identified? If the inductor is placed on the load side, so we can identify it as a buck converter. Now let me draw the buck converter here. So here for that, so a switch S1, right? Let me call this as S1. So we have the shunt switch S2. In the load side, we have the inductor and the capacitor and resistor. Right? So let it be the Vs. Let us see what is steady state of the converter. So here we are assuming that inductor is L and capacitor is C and the load is resistive load and output voltage is V0. Let us assume that IL is like this. So VL is assumed in this direction, positive in this direction. So IC is in this direction. Now, so let me draw the inductor current of the converter. So how can we draw the inductor current of the converter? So let us see. So here let us see how can we draw the inductor current. Let me draw the inductor current. So that you can understand clearly. Inductor current IL. How could I draw the inductor current? So for example, so VL equal to L di by dt, as we know that VL equal to L into di by dt. Right? So from this, if I can find the IL, which is equal to 1 by L into integration of VL into dt. Right? So this is the basic equation we have learned in the electrical circuits itself. So now I need to draw the VL. So if I know the VL, so I can draw the IL easily. So for example, assume that Assume that in a first cycle, this is the turn on period dt1. Let me assume that this is the dt1. The first cycle time period is assumed as t1. So what happens? The inductor current, initially the capacitor is at 0 voltage. It doesn't have any stored energy, so that it starts from 0. It starts from 0. When switch is S1 is in on condition, so S2 is in open condition, and here S1 and S2 are the complementary switches. So S1 is equal to S2 complement. What does it mean? When S1 is in on condition, S2 is in off condition. When S2 is in on condition, S1 is in off condition. So that S1, S2 are the complementary switches. If I want to switch on the S1, so S1 is controlled by the dt. So when S1 is in on condition, what happens? So the inductor current VL equal to inductor voltage equal to Vs minus V0. So Vs minus V0 by L is the slope. Vs minus V0 by L is the slope, right? So after that, it will be the, when switch S1 is in open condition. After this period, this is the off time of the switch. During the off time of the switch S1, S2 is in on condition. So this circuit will be isolated. Only this circuit we had. So the inductor voltage is equal to minus V0. During that time, it is minus V0. The slope is negative. The slope is negative because now the capacitor has charged to some voltage, right? So that it will increase up to some cycles. For example, let it be the T2 cycle. So up to some cycles, so somewhere at some point, the converter reaches to steady state. So during that state, the inductor current will be like this. Let me draw with a different color so that you can understand. So it will be like this. The steady state inductor current will be like this. At some point, it will be like this. So for example, if I take this as IL of T1, this point is IL of T1. This point is IL of T1. Right? So let us assume that small T1. What is this time period? That is switching period of the converter. So switching period of the converter. T. So which is IL of T1 plus T. If you observe in this condition, during the steady state, IL of T1 equal to IL of T1 plus T. IL of T1 plus T equal to IL of T1. So during the steady state condition, the converter is operated in steady state condition. So this condition should be satisfied. This condition should be satisfied. Similarly, if you draw the capacitor voltage also, the capacitor voltage also Vc of T1 equal to Vc of T1 plus T. During steady state operation, so the converter will be operate like this. Because in a transient condition, to analyze the buck or boost or buck boost converter, it is quite difficult. So that we are assuming that converter is operating under steady state. Converter is operating under steady state. We are not considering initial transient condition, so we are taking directly to the steady state condition. So let us see the next one. So the voltage ripple is negligible. The voltage ripple is negligible. So the voltage ripple is negligible. So right. So these are all the four assumptions. Main four is the buck converter, boost converter, and buck boost converter. So now let me start with the realization of the switch. What does it mean? So here we had drawn with the normal switches like SPST switches. Let us replace that switches with the power electronic devices. How can we realize the buck converter, boost converter, and the buck boost converter? Let us see here. So here, let me take the buck converter now. Let me take the buck converter, and then let me realize the buck converter, boost converter, and buck boost converter. So now let me draw the circuit first. So how is the circuit here? So here the switch S1 is there, the switch S2 is there, right? The switch S2 is there, S1, S2, and then in the load inductance will be there, so the capacitance will be there, and resistance is there, right? This is the circuit of the buck converter. Now, let us realize these two switches. That means these switches should be replaced by the power electronic devices. For that, we need to find the current flowing through the switch. We need to find the voltage across the switch during off condition. So now let us see. So it is Vs, right? So this is L, VL, plus minus VL, capacitor C, IC is the current flowing through the capacitor. So I naught and plus minus V naught. So now let us analyze this switch. So here during 0 to dt period, what we have assumed, during 0 to dt period, the switch S1 is in on condition. The switch S1 is in on condition. Switch S1 is in on condition. In all the cases, switch S1 is in on condition. Now, let me assume this. Let me take the different color. So let me assume this as common point O. So the point at which the two switches are connected to the inductor, so I am assuming it as a common point. And the IL is, I am taking as a reference. The current direction IL, I am taking as a reference. So this point I can call it as a 1, and this point I can call this as a 2. Now, let me find the I10 polarity. I10 polarity. So I10 in the direction of IL, because the current direction in the inductance does not change suddenly. So here if I take the current direction of the IL as a reference, I10 is also positive. I10 also is positive. Now, for example, if I take the V10, how the V10? So the V10 is, during the V10, how we can find the V10? Listen carefully. To find the V10 polarity, we need to turn off the switch. S1. So that is S1 should be in the off condition. So during that time, so what we need to do? So S2 is in on condition because S1 and S2 are the complementary switches. Right? So now make the S1 into off condition, S2 into on condition to find the V10. So now what is the V10 polarity? V10, the negative is connected. So with this switch is in on condition to the O and positive is connected to the 1. So 1 is connected to the positive terminal and minus is connected to the negative terminal. So V10 is negative. V10 is negative. Now, if I draw the VI characteristics of the switch, so how it would be? So if I draw the VI characteristics of the switch, the voltage is positive and the current is also, voltage is positive, current is also positive. So V10 is also positive. So both are positive. So the switch should be, if voltage and current both are positive, the switch can be transistor, IGBT or a MOSFET. So any of the switch you can replace with the S1. Now let us find S2. Let us find for S2. So when will be the S2 is in on condition? So 0 to, that is D dash T, during the period of D dash D to T, dt to T, that is D dash T period, that is 1 minus D into T period, the S2 is in the on condition. S2 is in the on condition. So during the on condition of S2, how the current direction will be? For example, if S2 is in on condition, how the current direction will be? So because the inductor current will not vary, direction is same, so the current direction will be 2 to 0. So that I20, that is current flowing through the switch 2, which is positive. I20 is positive. So now we need to find the V20. How can we find the V20? What does it mean? V20 is the voltage rating of the switch. V20 is the voltage rating of the switch. How can we find the voltage rating? During off condition of the switch, how much voltage it can withstand, which is equal to V20. So we need to off the switch S2 during this to find the V20. So V20, we need to off the switch. So during that time, S1 is in the on condition. Now let us find the V20 polarity. V20 polarity. So during that time, the positive is connected to O. Now what happened? The positive is connected to the O because S1 is an on condition when S2 is an off condition. So positive is connected to O and negative is connected to the 2. So now if I find the V20 which is equal to minus Vs. So the minus Vs will apply across the here. So here the plus Vs is applying across the switch S1. So here if I draw the VI characteristics of the switch, so how it would be? If I draw the VI characteristics of the switch, so the voltage is negative, which is equal to minus Vs, and the current direction is positive. So positive axis, right? Current is positive. So which device we can replace? This characteristic can be exhibited by the diode. Now, if I draw the buck converter, so how it would be? So now let me draw the buck converter. The buck converter circuit would be the switch S1. Let me call this as S. This S can be either IGBT or MOSFET or the transistor. So now we need to draw the S2. So S2 will be the diode. In which direction the current flows? In this direction, because what happens? The inductor current direction will not change. The diode has to conduct in this direction, upward direction. So the diode should be in this direction. Right? The diode should be in this direction. Now, the inductance is connected on the load side. So capacitance will be there and the resistance is also there. So this is the circuit diagram of the buck converter. This is the circuit diagram of buck converter. IL, IC, I0 and V0. So let it be the resistive load R. Right? This is the circuit diagram of the buck converter. And this switch can be replaced by the IGBT or MOSFET or IGBT or transistor. Now, let us see the second one. What is the second circuit? The second circuit is the boost converter. Now, let us find for the boost converter. Same analysis, let us apply for the boost converter. So, how the boost converter circuit will be? The boost converter circuit is identified if the inductor is connected on the load side. We can identify it as a boost converter. Now, let me draw the boost converter. So if the inductor on the source side, inductor should be source side, and the shunt switch should be at the source, and series switch should be at the load. This is the circuit we have for the boost converter. Right? Vs, inductance L, switch S1, switch S2, right? Capacitance C, resistance plus minus V0. So this is the circuit for the boost converter. Let us assume the inductance current is IL, which is equal to source current direction, right? So now capacitor current direction is assumed in this direction IC. So load current direction is assumed in this direction. Now let us find S1, 0 to dt period. Let us realize the switch S1. So this is the S1. Common point is assumed as O. Let me different with other color. So this common point is assumed as O. And this switch is assumed as 1 and O. And this switch is assumed as 2O. Now, 0 to dt. So S1 should be in the on condition. S1 should be in the on condition. When S1 is an on condition, so what happens? When S1 is an on condition, What will be the current direction? I01 in this direction. Let us take the inductor current as a reference. The inductor current is in this direction. Let us assume that I10, not I10, will take the I01. So I01 is the positive. So based on that, find the V01. How can we find the V01? So V01 is nothing but voltage rating of the switch. The capability at which switch can withstand, or how much voltage it can withstand. So we can find from the V01. Now we need to find the V01. To find the V01, what we have to do? To find the V01, we need to close the switch S2. Now let us close the switch S2. Now let us close the switch S2. Let me close the switch S2. Find the V10 polarity. So what is the V10 polarity? So the V10 polarity is, if I close the switch S2, what happens? So the polarity will be, the negative is here, and the positive is here, So V01 is positive. V01 is positive. If I draw in the graph, so let me take it as a V01 and I01, right? Both voltage and current are positive. So S1 can be replaced. This S1 can be replaced by the either transistor, MOSFET or IGBT. Let us see for the S2. So let us analyze for the S2. How can we analyze for S2? So S2. Now let us analyze for the S2. So how we can analyze for S2? So if you take the S2 switch, so here I need to find the I02. What is the I02 direction? So the inductor current, and this is the current entering into the 0 and leaving the 2. So I02 is positive. Now we need to find the V02. So how we can find the V02? So the V02 is, so to find the V02, I need to close the switch S1. So now if I close the S1, what happens? So here the negative is connected to the O, and 2 is connected to the positive. Now V02 is the negative. So from this, if I draw the V02 and I02, so the V02 will be mapped to the negative and I02 is positive. So this S2 can be replaced with the diode. So now let us draw the boost converter. So how the boost converter would be? Let us draw the boost converter. So now if I draw the boost converter, so the inductance will be here. This is the switch S, which can be IGBT or MOSFET or transistor. So now we have the diode. At S2, and in which direction it has to be? In the inductive current direction. So it should be like this. So we have the capacitance and the resistance. And this is the Vs. Right? Now S2 can be changed into diode and S1 can be replaced by the IGBT, MOSFET or transistor. So now let us see the next one. Buck boost converter. Let us see the next one, buck boost converter. So how the buck boost converter would be? In the buck boost converter, so the inductance is in between the source and load. So the switch S1 is in here. Switch S2 is here. And the capacitance and the resistance is here. This is the circuit, right? Let me call this as S2. and this is the Vs, L. Let us assume the inductor current direction in this direction, IL. So here the capacitor direction will be assumed in this direction, and I naught is also assumed in this direction. To get the, when you derive the expression, if you assume in this direction, you will get the positive output voltage. You will get the positive output. Otherwise, you will get the negative output voltage, right? So if you assumed in this direction the voltage, you will get the positive direction, right? Now let us find for the S1. So let us find for the S1. S1. So now the common point, as usual, the common point is assumed as O, and this point is assumed as 1, and this point is assumed as 2. Now let us find the I10 direction. So I10 direction, when S1 is in one condition, what happens? The current I10 is same direction of the inductor current, so it is positive. I10 is positive. So how can we find the V10? V10, how can we find the V10? So the V10, we can find V10, we can find, that is V10 here. We can find here. So how can we find? So for that you need to close the switch S2. If S2 is closed, minus is O and 1 is positive, 1 is connected to the positive, minus is connected. If S2 is closed, minus is connected to the O, so V10 is positive. If both are positive, if I map the voltage and current V10 and I10, so both are positive, so we can, S1 can be replaced with either transistor or MOSFET or IGBT. So similarly, let us do the analysis for the S2. Let us do the analysis for the S2. So now, if I take the S2, how can we? So for that, let us find the I20 now. I20 direction. I20 direction. So now, for that, S2 should be in the closed condition, S1 should be in the open condition to find the I20. So when S2 is in closed condition, so the inductor current direction will be in this direction. The current is flowing from 2 to 0. The current is flowing from the 2 to 0. That is I20 is positive. Now let us find the V20. V20. Let us find the V20. How can we find the V20? So here, to find the V20, what we need to do? We need to close the switch S1. So let us close the switch S1. If I close the switch S1, O is connected to the positive and 2 is connected to the negative. So what is the V20? So the negative voltage is applying. So V20 is negative. So we can replace with the diode. So V20, diode blocks the negative voltage. So which is equal to V20 is a negative, V20, I20. So V20 is negative, I20 is positive. So S2 can be replaced by the diode. In which direction it should be? Inductive current direction. In this direction, opposite direction. So anode should be in that direction, right? So now let me draw. So here, if I place the diode should be in this direction. Because the inductive, to allow the inductive current, the diode should be in this direction. So now let me draw the circuit here. Let me draw the circuit here. So if I draw the buck boost converter, how the buck boost converter would be? The inductor is at center, right? The switch S is replaced by the S, either IGBT or MOSFET or transistor. So here the source is connected, right? Now, so here the diode is connected and the diode direction should be opposite direction. Capacitance and the resistance. So this is the circuit for the buck boost converter and this is the circuit for the buck converter. This is the circuit for buck converter and this is the circuit for boost converter and this is the circuit for buck boost converter. So now let us solve some problems based on this. Let us solve some problems based on this. So this is the previous problem. I think it is not visible. Extend this one. So this is the previous question. Let me read the question. For a DC to DC boost converter, the order of the components LCD, that is MOSFET is the switch between supply and load from left to right. From left to right is, so how the L is connected, how the C is connected, how the D is connected. So let us see. So the first element is L. Definitely the first element is L. So L should be connected in. So L is connected in series, right? L is connected in series, and the switch is connected. MOSFET is connected in parallel. So the capacitance is connected in parallel, right? The diode is connected in series. So L is connected in series, diode is connected in series, C is connected in parallel. Now let us see. So which option is right? Let us see. So L, the third option, see the C option. So where L is connected in series, switch is connected in parallel, diode is connected in series, and capacitor is connected in the parallel. So option C is the right option. So now let us see the next question. So here a power converter is shown in the figure. Switching devices, namely X and Y. The source voltage is given as 50 volts. And the inductor current in steady state is 5 amperes without any ripple. So they need the VI plane. How the VI plane of the switches? Already we have derived. So the switch S1, that is X switch is S1, and Y switch is S2, right? How the X switch will be? Voltage and current both are positive. So voltage and current both are positive, which is equal to voltage and current both are positive. And the Y switch will be, that is switch S2 will be, if you see here, the switch S2 will be, in case of buck converter, let us see. In case of buck converter, if you observe here, so the voltage is, the current is, for the switch 2, the current is positive and voltage is negative. So the current is positive and voltage is negative. So correct this as minus 50 volts. So this is the diode, the switch, the second switch is the diode, and the first switch is the either IGBT or MOSFET or a transistor. Right? So this is the buck converter VI plane of the switch S1 and switch S2. Where X is the switch S1, so Y is the switch S2. Right? So now let us start the analysis for the three converters. So first, let us find the VL, that is voltage across. Let us find the VL and IC. So which is most important to find the remaining parameters. How we can find the VL and IC? Let us see. So first let me take the buck converter here. So and then let us find for the boost converter and buck boost converter. So here, so let us consider now 0 to dt period. First consider the 0 to dt period. So during the 0 to dt period, which is nothing but turn on time of the switch, during the turn on time of the switch, this S should be in the closed condition. So the diode should be in the off condition. This diode is in off condition and the switch is in L, switch S is in the closed condition. We need to find the voltage across the inductance and the current flowing through the capacitor. Let me find the voltage across the inductance. So what is the voltage across inductance? 0 to dt when switch is in closed condition, the plus Vs, so the plus Vs is applying here, right? So and minus negative is here. So here, so what is the voltage across inductance? So Vs minus Vs plus Vl plus V naught equal to 0. If I write the expression minus Vs, if I apply the KVL in that loop, plus VL plus V naught equal to 0, which is equal to VL equal to Vs minus V naught. VL equal to Vs minus V naught. So the voltage across inductance when switch is in closed condition, so which is equal to this one. So now let me find the IC. So what is the IC value? So what is the IC value now? So IC equal to IL. So let me call this as I naught. So which is equal to IL minus I naught. So IL is entering, IL equal to IC plus I naught. So from that, if I find the IC, which is equal to IL minus I naught. So which is equal to IL minus I naught. Right? During the D0 to dt period. Similarly, let us find for the period of dt to t. So during the dt to t, what happens? The switch S1 is in the off condition. The switch S is in off condition. Diode D is in on condition. Diode D is in the on condition. So now let us analyze for this. So when diode D is in on condition, so the circuit is completely isolated. So VL equal to, so see here, plus minus is connected to the plus of V naught. So VL equal to minus V naught. VL equal to minus V naught. So if I find the IL equal to, so IC equal to IL minus I naught. IC equal to IL minus I naught. Very simple, right? So VL equal to minus V naught. So minus V naught. So here 0 to dt period and dt to t period. Similarly, let us find for the boost converter. So let us find for the buck boost converter. So now let me take the boost converter. Now let us take the 0 to dt period. 0 to dt period. What is the condition 0 to dt period? The switch S is in on condition and the diode is in off condition. Right? So when switch S is in on condition and the diode is in off condition, this circuit is completely isolated, right? So now VL equal to, see here, the positive of the VS is connected here and from negative of the VL is connected to the negative of the VS. So it is VL equal to VS. Right? Now we need to find the IC. So how can we find the IC? IC equal to, let me call this as the I naught. IC plus, this one is open condition. Now it is open condition. So for at this node, IC plus I naught equal to, IC plus I naught equal to 0. So IC equal to minus I. IC equal to minus I. Now let us find dt to t period. So dt to t period, what happens? The switch S is in off condition. Diode is in on condition. So S is in off condition. Diode is in on condition. So now let us find the VL. So VL equal to Vs minus V naught. So VL equal to Vs minus V naught. And what is the IC value? So the IC value is, so now in this circuit IC value is, so this one is IC. So IL minus I naught. IC equal to IL minus I naught. Similarly, let us find for the buck boost converter. How we can find for the buck boost converter? So here, again, same principle. Let us take the 0 to dt. Right? 0 to dt, what happens? The switch S is in closed condition and the diode is in open condition. So the circuit is completely isolated. Right? Now what is the Vs? So here the inductive voltage is source voltage. VL equal to Vs, right? Now let us find the IC. So this is open circuit. IC plus I naught equal to 0. IC equal to minus I naught. IC equal to minus I naught. Now let us find for the dt to t. So during the dt to t period, what happens? The switch S is in open condition. The diode is in on condition. So when diode is in on condition, what happens? This circuit source is isolated now. So diode is in on condition. So VL equal to minus V naught. VL equal to minus V naught. VL equal to minus V naught. Now, so what is the IC value? IC value, IC equal to, now the inductor current is also flowing. So here inductor current is also there. Inductor current is also there. So I naught equal to IC plus IL. So IC equal to IL minus I naught. IC equal to IL minus I naught. Now we have derived for the three cases. Now we have derived for the three cases. Let us see. So the series, the same principle we are applying. So what we have done here, 0 to dt, switch S is in on condition, diode is in off condition. We find the VL and IC. So next, dt to t, what we have done? So we find the VL and IC. So switch S is in off condition, diode is in on condition. So these three conditions we have derived. Now let us go further. So here, so now let me fill this table. Already we have derived. So here, in case of buck converter, 0 to dt, what is 0 to dt? Which is equal to Vs, VL equal to Vs minus V naught. dt to t, it is the Vs, VL equal to V naught. So VL equal to V naught. So now, what is the IC value? Which is equal to IL minus I naught. IL minus I naught. So here it is IC equal to IL minus I naught. See here, we have find already. So here VL equal to minus V naught. So IC equal to IL minus I naught. It is minus V naught, right? So now, so from that conclusion, so let me fill this table. So 0 to dt. So what is the VL value here? So VL equal to Vs. So what is dt to t? So which is equal to Vs minus V naught. Vs minus V naught. So here IC equal to minus I naught, and here IC equal to IL minus I naught. So here, in case of buck boost converter, 0 to dt period, it is VL. So VL equal to Vs, and dt to t is the minus V naught, right? So similarly, IC is minus I naught, which is equal to IL minus I naught. IL minus I naught. So I think we have done correctly, right? So IC equal to IL minus I naught, VL equal to VL. So now we have filled this table. Now it is easy. If you know these values, that is sufficient for the remaining analysis. So let us find the relation between the V naught and Vs. Now let us find the relation between the V naught and Vs. V naught and Vs by applying the volt-second balance. So what is the volt-second balance? In case of steady state operation of the converter, so integration of VL into dt equal to 0. The charging area is equal to discharging area. Integration of VL into dt equal to 0. Integration of VL into dt equal to 0. So in case of volt-second balance, let me apply the volt-second balance here so that you can understand. So here, so now let me draw the curve here. So let me draw the graph here for the VL. So now let me draw the curve for the VL. Let me take the time is an x-axis, VL is an y-axis. So 0 to dt, that is on time of the switch, dt. And the remaining period will be the total time. So 0 to dt, right? This period will be the dt, right? 0 to dt, what is the VL? Which is equal to Vs minus V naught. Vs minus V naught. So in case of buck converter, V naught is less than the Vs, so it will be the Vs minus V naught. This magnitude will be the Vs minus V naught. Now dt to t. So that is 1 minus d into t. This period will be the 1 minus d into t. And this period will be the dt. Now, so what is the condition here? VL equal to minus V naught. VL equal to minus V, which is minus V naught. So apply the old second balance. What is the old second balance? If you find the net area, which should be equal to 0. If you find the net area, which should be equal to 0. So if you find the net area, so how can you find the net area? So here this area we need to find, and this area we need to find. This area we need to find. If you find the total area, it should be 0. What is the total area? So the area of the rectangle, which is equal to Vs minus V naught into dt. Let me solve for the buck converter so that you can solve for the remaining converters. So plus minus V naught into d dash t. We can call this as a d dash t. D dash t, where d dash is the 1 minus d. So which is equal to 0. Which is equal to 0. If I done this, which is equal to Vs into d, Vs into d minus V naught into d minus V naught into d dash. So that is equal to V minus V naught into d plus d dash. So d plus d dash equal to 1. So d plus 1 minus d equal to 1. So minus V naught equal to 0. V naught equal to, from that V naught equal to, so what is the value of V naught? V naught equal to, so V naught equal to Vs into duty cycle. The duty cycle in between the 0 to 1. So this is for the buck converter. So now let us do for the boost converter. Same analysis let us apply for the boost converter. So what we have to do? We need to apply the old second balance to get the output voltage of the converter. So what is the old second balance? Integration of VL into dt is 0. That is charging area plus discharging area. If you combine both, it should be equal to 0. So now if I apply for the boost converter, how can I apply? Vs into dt, right? Plus Vs minus V naught into d dash t. That is 1 minus d into t. 1 minus d into t. So if I apply this one, so Vs, t and t will get cancelled out if I go there. So it will be Vs minus V naught into d dash. So from that, V naught equal to Vs by d dash, where d dash equal to 1 minus d. Right? So V naught equal to Vs by d dash. V naught equal to Vs by d dash. Similarly, so let us apply for the buck boost converter. So how can we apply for the buck boost converter? So now let us take the VL, only VL. So what is the VL here? So VL is the area of VL, Vs into dt, right, minus V naught into d dash. T will get cancelled out. So which is equal to V naught equal to Vs into d by d dash, where d by d dash, where d dash is the 1 minus d. D dash is the 1 minus d. Right? So now we got the three. We derived the output voltage for the three converters. So what is the buck converter output voltage? V naught equal to Vs into duty cycle. What is the boost converter output voltage? V naught equal to Vs divided by 1 minus d. And in case of buck boost converter, V naught equal to Vs into d by 1 minus d. So these three expressions are much important. Now let us go for the next slide. Now, so this was the problem. It was given based on the topic, based on the concept. So here, for the converter shown in the figure, what is this converter? First we need to observe what is this converter. So what is this converter? The inductor is placed on the source side. The inductor is placed on the source side. Inductor is placed on the source, which is boost converter. right? So it is the boost converter. Now, what they have given? VL. This is the VL. So this is VL. VL waveform they have given. VL waveform they have given. So what we need to find? So we need to find the duty cycle of the switch. So how the VL waveform of the buck and boost converter? So VL waveform of the boost converter will be like this. If I draw the VL waveform of the boost converter, 0 to dt period, 0 to dt period. For example, if I draw the boost converter 0 to dt period, that is d into t period, so which is equal to Vs, which is equal to Vs, and dt to t period, so which is equal to Vs minus V0. If you know the fundamental, so you can find from this. There is no calculator is needed, that's why I included this problem. So it was given as 15 volts. So Vs is given as 15 volts and Vs minus V0 is given as minus 45 volts. Minus 45 volts. Now, so let us find this. Let us find this. So Vs minus V0 is given as minus 40. Now what is the V0 value? So Vs is given as 15. 15. If minus 45 come this side, so what happened? Then this side what happens? So it will be the 15 plus 45. So V0 equal to 60 volts. Now we got the V0 value and Vs value. So now we have the Vs. We got the Vs as 15 volts and V0 is the 60 volts. So now we need to find the duty cycle. How can we find the duty cycle? So very simple. V0 by Vs. V0 equal to Vs by 1 minus d. Vs by 1 minus d. So 1 minus d equal to Vs by V0. So what is the Vs value? 15. So what is the V0 value? 60. So which is equal to 1 by 4. 1 by 4 in the sense 0.25. So from that duty cycle equal to 0.7. There is no calculator is required. There is no calculator is required. So directly you can answer if you know the concept. So we have derived from this. So we got the in a boost converter. If you know this table, that is sufficient. If you know this table, that is sufficient. So now let us solve the next one. Now let us find the relation between the I0 and IL. Let us find the relation between the I0 and IL. So where I0 is the steady state output current. Let us assume that it is a steady state output current. IL is the average inductor current. So let us find the output current and the average inductor current. So we need to find the relation between two. So let us find the relation. So how can we find? So again, let me fill this step. So what is the VL in case of buck converter? So in case of buck converter, it is 0 to dt, it is Vs minus V0, and dt to t it is minus V0. So what is the IC value? So which is equal to IL minus I0. So which is equal to IL minus I0, and it is so VL. So VL is so 0 to dt, here it is Vs, and it is Vs minus V0, and IC is minus I0, and it is IL minus I0, right? It is IL minus I0. So here 0 to dt, it is Vs, and it is minus V0, and it is minus I0, and it is IL minus I0. This we already derived. This we have already derived. Now we need to find by applying the Ampere-second balance. What is volt-second balance? So the voltage across inductance, integration of VL into dt equal to 0. The area of the inductor voltage, if you find that, it is 0. So similarly, the Ampere-second balance is nothing but so integration of IC dt equal to 0. Integration of IC dt equal to 0. So by applying the Ampere-second balance, we can find the relation between the IL and IL. That is average value of the IL and the load current. Now let us find for the buck converter. So how can we find the average value? So to find the relation between the I0 and IL, so we need to find the IC. So we have already determined the IC here. So let me write the expression. So how we can write in a similar manner. So IL minus I0, let me take the average values here. IL minus I0 into dt plus IL minus I0 into d dash, which is equal to 0. In both cases it is, so in both the cases it is, so IL minus I0. So dt to t period also it will be the IL minus I0. So if I take t and t will get cancelled. So both are same. So IL minus I0 into d plus d dash. So into d plus d dash, which is equal to 0. So as we know that d plus d dash equal to 1, so IL equal to I0. IL equal to I0. So from this IL equal to the average value of the inductor current equal to I0. So now let us find for the boost converter. In a similar manner, let us find for the boost converter. So how we can find for the boost converter? So minus I0, very simple, minus I0 into, during the time period of dt, it is minus I0 into dt, the area will be, so IL minus I0 into plus IL minus I0 into t dash, which is equal to 0. And t will get cancelled out, right? So minus I0 into d plus d dash, so that minus I0 and plus IL into d dash, so which is equal to 0. So from this IL equal to I0 divided by d dash. So I0 divided by 1 minus t. So this is the expression for the IL. This is the expression for IL. That is inductive, average inductor current. Now let us find for the buck boost converter. If you see this, both are same. So 0 to dt period minus I0, dt to d period IL minus I0. So both are same. So the expression also same, no need to find, which is equal to I0 by d dash, where d dash is the 1 minus d dash is 1 minus, right? So now we have derived for the IL and I0 also. So now let us find the current ripple. What is the current ripple? That is delta IL. Delta IL we need to find. So let us find the current ripple for the buck converter. Right? So let me fill this table. Already we have derived. Let me fill this table. So how can we fill this table? So 0 to dt, it is VL equal to Vs minus V0, and dt to d it is minus V0. Right? So IC value is, it is IL minus I0. So here also it will be IL minus I0. So now let us find how to find the current ripple from the IL waveform. So for that we need to draw the IL waveform. So let us see how we can draw the IL waveform. So let me draw the IL waveform. So that you can understand easily. How the IL waveform should be? So initially I have discussed. So it is IL, waveform of the IL. So during the on time of the switch, the inductor charges, right, with the slope of Vs minus V0 by L, right? So during the dt period. In the remaining period, what happens? During the off time of the switch, the inductor discharges to the load. So it will be the, so what is the slope here? Minus V0 by L. Right? So this is the time period T. For one cycle, it will be like this. So both are same. Both are at same, because during the steady state value, these two are at the same point. So we can call this as I minimum. I minimum. And we can call this as a I max. So this is the IL waveform. This is the IL waveform. Simple. IL equal to, so IL equal to, so VL equal to LdI by dt. So IL equal to 1 by L into integration of VL dt. So IL equal to, as you seen that, IL equal to LdI by dt. So VL equal to LdI by dt. Right? So di by dt equal to, what is the slope? VL by L. Di by dt is the slope, that is delta I. We need to find this one, delta IL. So which is current ripple, right? So from this di by dt equal to VL by L. So what is the slope during the 0 to dt? So which is equal to Vs minus V0 divided by L. 0 to dt, the value of the VL is Vs minus V0. So if I want to find the slope, it will be the Vs minus V0 by L. So now, after dt to d, that is turn off time of the switch, what happens? So the current, the output voltage is negative, so the slope will be negative. The slope in the decreasing nature, so which is equal to minus V0 by L. Now, we need to find the delta IL. We need to find the delta IL. How we can find the delta IL? So delta IL is, let me represent with the other. So delta IL is from here to here. This portion is the delta IL. So this is the delta IL. This is the delta IL. How we can find? So delta IL is simple. So simple, which is dt. From here to here it is dt. So the slope will be the Vs minus V0 by L, and it will be the minus delta IL. So how we can find? So delta IL equal to delta IL divided by, so y-axis is the delta IL, so x-axis is the 0 to dt. 0 to dt, if I consider dt minus 0 is the delta t, so which is equal to dt, which is equal to dt, y2 minus y1 by x2 minus x1, so which is equal to slope Vs minus V0 by L. Simple. Slope we have find, Vs minus V0 by L. Now, let me find the remaining things. From this, we can find the delta I. From this, we can find the delta I. So here, understanding the concept is important. So here, how you can find the delta IL? From this, delta IL equal to Vs minus V0 divided by L into dt, into d into t, where t is the time period of the switch. So we can make it as a 1 by f. 1 by f. So V0 equal to Vs into duty cycle. Already we have derived. In case of buck converter, V0 equal to Vs into duty cycle. If I find that, so Vs, if I substitute here Vs into duty cycle, if I take the common, Vs into d into 1 minus d, d into 1 minus d, divided by, so if I take the t equal to 1 by f, so which is equal to L into f. Which is equal to L into f. So now, if I want to find the duty cycle at which the current ripple is maximum. Now we got the expression for current ripple. So you need to remember this waveform and the current ripple also. Now let us find the delta IL max with respect to duty cycle. So though delta IL by d I need to find, which should be equal to get the maximum value, it should be equal to 0. So if I find that, so these terms will be Vs by Lf is constant. So d minus 1 minus d is the, so if I derive this one, dou by dou d into d minus d square, so which should be equal to 0. So that is 2d minus 1 equal to 0, d equal to 0. At duty cycle equal to 0.5, this point is important. At duty cycle equal to 0.5, so the delta IL will be the maximum. Delta IL is the maximum current ripple. So now, let us find the remaining things. So now if I find the delta IL maximum magnitude, so what is the thing? I need to substitute the 0.5. So that is 1 by 2 into 1 by 2, 1 by 4. That is equal to Vs divided by 4 into L into F. So which is equal to Vs divided by 4 into L into F. So which is equal to 4 into L into F. So we have find the delta IL also. Now let us find for the boost converter. So let us take the boost converter now. So here if I take the boost converter, so what is the current ripple? If I take the boost converter, so let me draw the, what we need to do? So we need to draw the IL waveform. We need to draw the IL wave. For that we need to know the VL. So which is equal to VS, VL equal to VS, and dt to t period it is the VS minus V0. In case of boost converter, V0 is greater than the Vs, so that Vs minus V0 is negative. So if I draw the same graph, it will be like this. It follows the same manner. But what are the slopes here? The slopes will be different. Let me take this as the dt period, and it is the t period. So this period will, up to here it will be the dt. So which is the I minimum, I maximum. So what is the slope here? So which is equal to Vs by L. This slope will be the Vs by L. And what is the slope here? So Vs minus V0 by L. And this slope will be the Vs minus V0 by L. What we need to find? Delta IL. How can I find the current ripple? So delta IL equal to, so delta IL by dt is the slope, so which is given as Vs by L, Vs divided by L. So from this delta IL equal to, so which is very easy, Vs by L into dt. Vs by L into dt. So we got the delta IL. So now let us find for the buck boost converter. So now you can find for the buck boost converter also. So now let us find for the buck boost converter. We need to draw the IL wave. So for that, let me fill this table. So what is the VL value here? 0 to dt, it is Vs. dt to t, it is minus V0. Right? So if I draw the graph, it will be the Vs by L, and here it will be the minus V0 by L. So it is, this slope will be the Vs by L, and this slope will be the minus V0 by L. Decreasing slope. So here it will be the period of dt period. dt, and this is the t period. Now find the same thing. So same analysis we need to find. We need to find the delta IL. How can we find the delta IL? So already we have determined. So it is easy for you. So how can we determine? So delta IL equal to Vs by L into dt. Vs by L into dt. Same, Vs by L into dt. So this is how we find the current ripple. So now let us see how this current ripple can helpful for you. So now let us see. So for example, so this was asked in the previous year question paper, AP Transco 2019. So this was asked in the 2019 AP Transco paper. So what it was given? Let me read. If it is not clear for you, let me read for you. So the DC to DC buck converter is given. The rate of change of current for the inductance value L is given as 400 microhenry. And L, the rate of change of current. The rate of change of current is nothing but delta IL divided by dt they have given. So the slope they have given. So what is that? So which is equal to, in case of buck converter, which is equal to Vs minus V naught by L. Vs minus V naught by L, right? So which is equal to Vs minus V naught by L. So how much they have given? So it was given as 7.5 into 10 power 4 ampere per second. Ampere per second. Now what we need to find? If the converter is operated with the input voltage 50 volts, Vs is given as 50 volts. Now what we need to find? We need to find the output voltage of the converter. We need to find the output voltage of the converter. So what is the output voltage we need to find? So already this was given 7.5 into 10 power 4. So let us do it here. So delta IL by dt is given. So which is equal to 7.5 into 10 power 4 into L. So we can get the Vs minus V naught equal to 7.5 into 10 power 4, right? So L is given as 400 microhenry, 400 into 10 power minus 6 microhenry. So this will be cancelled out. 7.5 into 4, which is equal to 30. So from that, so Vs is given as 50 volts. So 50 minus 30, which is equal to V naught. So V naught equal to 20 volts. So very simple. But you should understand the basics. You should understand the basics. What is slope? So what is the slope of the line? So what is the expression for the delta IL? If you know the direct delta IL expression also, you can substitute. So you can substitute here, right? Now let us see the next question. So here it was given as step down chopper. So the calculator is not needed here also. So it is given as step down chopper in the figure. So switched at the 1 kHz. The frequency is given as 1 kHz. So duty ratio is given as 0.5. So peak to peak ripple load current. They want peak to peak ripple load current. Peak to peak ripple load current. So here they asked for the ripple load current. So but we know the delta IL, ripple inductor current we know. Is both are same. So in this circuit, observe here. So IL equal to I naught. So delta IL equal to delta I naught. In this circuit, delta IL equal to delta I naught. So they want the peak to peak ripple load current, which is equal to delta IL they want. So we need to find the delta IL here. So here duty cycle is given and input voltage is given as 100 volts. So Vs is given as 100 volts. And L is given as 200 millihenry. L is given as 200 millihenry. Now we need to find the delta IL. Simple, delta IL. So what is the delta IL? So which is equal to Vs into D into 1 minus D. You can directly substitute the formula. So divided by L into F. So here, so Vs is given as 100 volts. And D is given as 0.5, that is 1 by 2. So 1 by 2 into 1 by 2, which is equal to 1 by 4, divided by 1 by LF. So L is given as 200 milli, 200 into 10 power minus 3, and F is given as 1 kilohertz. So that is 10 cube. These two will get cancelled out. So you need to find the delta IL. So here this will be cancelled out. So 1 by 4 is the 0.25 ampere, right? So delta IL equal to 0.25 amperes. So direct formula you can apply. Voltage ripple. So voltage ripple can be found from the IC waveform. So let us see how the IC waveform can be drawn. So here to draw the IC waveform, so we need to know the we need to know the IC values. 0 to dt. So what is the IC value in buck converter? So which is equal to IL minus I naught. IL minus I naught. So dt to D also, which is equal to IL minus I naught. So both are same, IL minus I naught. So in case of the boost converter, what is the value? So in case of boost converter, so which is equal to 0 to dt, so which is equal to minus I naught, and dt to t, it is IL minus I. So in case of the buck boost converter, so it is same, so minus I naught, so which is equal to IL minus I. IL minus I naught. Now let us draw. Now let us draw IC waveform for the buck converter. How we can draw the IC waveform for the buck converter? So here, let us draw the IC waveform for the buck converter. So what is IC here? So IC equal to IL minus I0. Already we know that how to draw the IL waveform. So for example, if I draw the IL here, if I draw the IL here, so how the IL will be? So the IL is, so it will be like this, right? So what is the slope here? So which is equal to Vs minus V naught by L. So which is equal to V naught by L. So this is the IL waveform that we already drawn. So now up to here the period will be the T and this period will be the T. The total period will be the T. So now let us see. We need to take the I naught value from this. So let me take I naught here. Let me represent the I naught with a different color so that you can understand. So I naught will be like this. So let me call this as I naught. So in case of buck converter, so during the starting we have derived IL equal to I naught. The average value of IL equal to the average value of I naught. So IL equal to the average value of IL. IL equal to I naught. So now we had an instantaneous value and the average value. Now we need to draw the IC waveform. How to draw the IC waveform? So IC equal to IL waveform minus I naught. So IL, when IL equal to I naught, so what happens during this time? So the current will be 0. When IL reaches to I naught, so IL reaches to I naught, so what happens? IC equal to 0. So during these 2 points, IC equal to 0. So this is the 0 axis, right? So IC equal to 0. So the waveform will be, the IL waveform will be shifted to the ground. So it will be like this. It will be like this. And this is the delta IL by 2. This is delta IL by 2. And this is also delta IL by 2. And the total peak to peak ripple of the IC is delta I. Right? So now we need to find the voltage ripple. So how we can find the voltage ripple from the current waveform? If I can find the charge, from that I can find the voltage ripple. So let me find the charge here. So how can we find the charge here? So here integration of IC dt equal to Q, right? Q equal to, so IC equal to dq by dt, as we know that from the fundamentals, IC equal to dq by dt, right? So for example, if I want to find the dq, so I need to find out the integration of IC dt, which is equal to delta Q, So now, so if I want to find the delta Q, if I want to find the delta Q, I need to find the area. So which is equal to T by 2, and this portion will be T by 2 because the charging area is equal to discharging area. So that this will be charging area and these two are the discharging areas. So here, if I want to find the charging area, what I need to do? The height will be the delta IL by 2, the base will be the T by 2. So half into area can be found from this one. So delta IL by 2 delta IL by 2 into T by 2. T by 2. So which is nothing but 1 by 8 into delta IL divided by F. So T equal to 1 by F. So this is the delta. This is the delta. Now, if I want to find the delta V, so as we know that, so delta Q equal to C into delta V. So if I want to find the delta V, so I need to find the delta Q divided by C. Now from the fundamentals, Q equal to CV, right? So if I want to find the delta V, I need to divide with the C. So which is equal to 1 by 8 is into delta IL divided by C into F. C into F. So which is equal to in terms of delta IL. So already we have derived the delta IL. If I substitute this, I will get the final expression. So what is the delta IL we got? So delta IL equal to, so delta V equal from this 1 by 8 into, so delta IL is the, so Vs into D into 1 minus D, right, divided by L into F. So I can write it into LC into F. So which is the voltage ripple expression for the this is the voltage ripple expression for the buck converter. So I can find the maximum voltage ripple also. How can we find? Similar to delta V max equal to, so I need to differentiate with the duty cycle. So with the D, so delta V by delta D I need to find. So if I find that, so at D equal to 0.5, similar to that, so I can get the maximum value. If I substitute D equal to 0.5, D equal to 0.5, that is delta V max equal to 1 by 32 into Vs divided by LCF square. So which is the expression for delta V max. So this we have already derived in the delta IL. In the same manner, we have to derive here also. Right? Now, let us find for the boost converter. So it is very easy. Let us find for the boost converter. So how can we find for the boost converter? So in case of boost converter, so if I draw the IC waveform directly I can draw. So IC waveform directly I can draw. Let me draw the IC waveform. Let me draw the IC. So what is the IC? 0 to dt. What is the value of IC? Which is constant, which is equal to minus I naught. So dt period, up to dt period. So dt to t, which is IL minus I naught, which is similar to the IL minus I naught, and this waveform will be like this. IL minus I naught. So which is Vs minus, the slope will be the Vs minus V naught by. So now, if you want to find the, so delta Q, so the charging area equal to discharging area. So if I take the discharging area, so which is equal to I naught into dt, so which is equal to delta Q, I naught into dt. So if I find the delta V, so what I need to do? I naught into dt divided by C. Simple. So we find the area, so we got the charge divided by capacitance, which is equal to delta. So similarly, let us find for the, so similarly, if I find this one also, for this one also, so it is similar. So similar expression I got, because IC waveform is similar, except this will be the minus V naught by L. Slope will be the minus V naught by L. So, but this expression also similar. If I find that this expression also similar, so the expression would be the, so delta V equal to I naught into dt by C. So I naught into dt by C, or I naught into d by F. Right? So we got the delta. We have derived the voltage ripple. let us see what is the application for this. So here each and every point is important. Each and every point is important. So for example, so let us find here. Let us find here. Let us solve this problem. So a chopper is employed to charge the battery. So battery is there, 12 volts battery is there. So it is employed to charge the battery. The charging current is 5 amperes. So charging current is given as 5 amperes. That is I naught is, let me take the I naught here. So which is equal to 5 amperes. 5 amperes, right? So now duty cycle is 0.2. Duty cycle is 0.2. Duty cycle is given as 0.2. And so Vs is given as 60 volts. Input voltage is given as 60 volts. So Vs is given as 60 volts. So VDC, that is Vs is given as 60 volts. And the remaining things, let us see. Remaining things, what are the remaining things? Let us see. So VDC waveform is given 60 volts. And the peak to peak ripple current of the charging current they need. So charging current, peak to peak ripple current is nothing but output current. So which is equal delta IL we need to find. For this delta IL we need to find. In a simplest manner, you can answer in a simplest manner. So here, so VDC value, the VDC is given is like this. The VDC is given as like. So we let us, VDC is the 60 volts. VDC is the, so the Vs is given as 60 volts. The input voltage is given as 60 volts. So what we need to find? So peak to peak charging current, delta IL we need to find. So how we can find the delta IL? So delta IL equal to, so Vs minus V naught. If I find the V naught from this, so Vs minus V naught divided by L into dt, right? So which is the expression for the delta IL? So I got the Vs is equal to, so Vs is equal to 5 amperes. So Vs is equal to 60 minus V naught is, so into duty cycle, which is equal to 60 into 0.2, so that is equal to minus 12 divided by, so L is the 20 millihenry, duty cycle is 0.2 into time is given as 1 millisecond. Millisecond and millisecond will get cancelled out. So this is 0.2 times 2 by 10, so which is 100. 60 minus 12 is the 48. So 48 divided by 100, which is equal to 0.48. Which is equal to 0.48 amperes. So now let us see the next problem. So now find the values of the diode current. Find the values of diode current. So we need to find the average value of the diode current. Average value of the diode current. So when will be the diode conducts? The diode conducts during the d-t time. d-t time. So here it carries the inductor current. It carries the inductor current IL, so which is equal to I naught. In case of the buck converter, which is equal to I naught. So I naught into, so which is equal to IL into the diode average current. If you find the diode average current, so IL into duty cycle, IL into D dash. The diode average current can be found as IL into D dash. So similarly, the diode RMS current, if I want to find, so which is equal to IL into square root of D dash. So let us understand clearly. So here IL equal to I naught. So if I draw the diode current, how can we draw the diode current? The diode carries the inductor current. Diode current is inductor current during the period of d dash t. Diode current is equal to, let me draw the diode current waveform so that you can understand. So the diode current waveform, if I draw the diode current waveform, so it will be 0 to dt, 0 to dt, it is 0, 0 to dt, the value of diode current is 0 because switch is in on condition, diode is in off condition. So during the remaining time, the diode will conduct the inductor current. So which is having the I max. Delta IL max is the, so IL max. So that is I max is the maximum current flowing through the diode. So if I find the average value IL, so IL average, if I find the IL average, so during the D dash T period only, it will exist. And here it will IL also be 0 because the diode current is 0. So only IL average exists only during this period, which is equal to D dash into T. So that if I find the average value of the diode current, IL into D dash. So if I find the RMS value of the diode current, it will be the IL into square root of D. So the maximum value of the diode current will be the maximum value of the inductor current. So in a simplest way, let me write here. In all the three converters, same expression. The average value of the diode current, equal to ID average equal to IL into D dash, where D dash is the 1 minus D. D dash is the 1 minus D. Right? D dash is the 1 minus D. So the RMS value of diode current equal to ID RMS equal to IL into square root of D dash. Simple, because it's a simple square waveform, so we can write it as square root of D dash. So now, so for example, if they ask for the maximum value of the diode current equal to inductor maximum current, ID maximum equal to the maximum value of the inductor current. So both are same. If you can find the maximum value of inductor current, you can find the maximum value of the diode current. So now let us see the next one. So based on this, let us solve one question so that you can understand. So what is the type of the converter? So here, inductor is placed at the load side. So if the inductor is placed on the load side, so it is related to the buck converter. Simple. Now it is buck converter. So what we need to find? The average value of the diode current. We need to find. So ID average we need to find. How can we find? So which is equal to IL into duty cycle. D dash, where D dash is the 1 minus D. Now, in case of buck converter, IL equal to I naught, so that average value of IL equal to average value of I naught. If I can able to find the I naught, so it is done. So the duty ratio is given as 0.8. So what is the VS? VS is given as 100 volts. So what is the V naught? V naught equal to VS into duty cycle. There is no calculator is required. So 0.8 into 100 is 80 volts. So now we got the V naught. So what is the I naught? So I naught equal to V naught by R. So V naught by R, so that is 80 by 10, so which is equal to 8 amperes. Now we got the I naught. So if you got the I naught, so now you can find the ID average value. So ID average is equal to 8 into 1 minus D. So what is the D value? 0.8. 1 minus D is the 1 minus 0.8. So which is equal to 0.2, which is equal to 1.6 amperes. 1.6 amperes. So now let us solve the next question. So let us solve the next question. So now, so what is the converter here? So it is the, what is the converter here? So it is the inductor is placed on the source side so that it is a boost converter. So now we need to find it for the boost converter. So how can we find for the boost converter? So let us. So it is the boost converter. So the switch is operated at the duty cycle of 0.5, which is operated at the duty cycle of 0.5 amperes. Right? So VDC is given as 20. VDC, that is input voltage, given as 20 volts. The current is assumed as continuous and it was given 0.5 amperes connected across the load. 0.5. So a large capacitance connected across the load. So IL is given. IL average already given, which is equal to 4 amperes. So directly IL average has given. So what they want? So what they want to find? So the average voltage across the load V0 and average current through the diode. So first let us find the V0. So in case of boost converter, which is equal to Vs by 1 minus V, right? So Vs is given as VDC. So VDC is given as 20 volts divided by 1 minus 0.5, which is equal to 40 volts. So V0 we got as a 40 volts. Now let us find the diode current. So ID average current. So if I find the ID average, so how can we find the ID average? So the diode current will be, so ID average equal to IL into D dash. So what is the IL they have given? 4. So what is the D dash? 1 minus 0.5. So which is equal to 2 amperes. Which is equal to 2 amperes. So 40 volts and 2 amperes is the answer. Because directly IL value has given. So directly IL value is given. So now let us solve the next question. Find the value of source current. How we can find the source current? So it is very easy. So here we are assuming that the converter is operating in the ideal condition so that P not equal to Pin. That is output power equal to input power. So V naught into I naught equal to Vs into Is. From that I can find the source current. So which is equal to V naught into I naught divided by Vs. The source current will be V naught into I naught divided by Vs. So from this we can find the source current. For all the cases we can find. So now if they ask for the switch current, so the switch will be conduct for D into T period. So which current it will take? IL current. So the switch current will be, if I draw the switch current, it would be like this. Let me draw switch current. For all the 3 cases it is similar. The values may change, but it will be similar. Waveform nature is similar. If I draw the switch current, I switch, during 0 to dt only the switch will conduct. Remaining period the switch will be in the off condition. So the switch is conduct for the 0 to dt. The switch is conduct for the 0 to dt. So it will be like this. 0 to dt. So the maximum current of switch current is equal to IL max. So this is depends on converter. So it is Vs slope is depends on the converter topology, but it is similar. So it is IL waveform. So IL average. The IL average will exist in between the. If I draw the IL average with a different color, let me draw the IL average with a different color. So the IL will be like this. So if I find the switch current average value ISW, so it is equal to IL into D, duty cycle. Whatever may be the topology, IL into duty cycle. So if I want to find the RMS value of the switch current, so it is equal to IL into root of square root of D. IL into square root of D. This is how we can find the average and RMS value of switch current. So the maximum value of the switch current is equal to, so the maximum value of the inductor current. Maximum value of the inductor current. So now let us solve the one question on this. So here it was given as buck converter because the inductor is connected on the load side. So simple, the inductor is connected on the load side. So it is a buck converter. Now, so the frequency is given, the peak current in the switch. The peak current in the switch. They ask for the peak current in the switch. The peak current in the switch. So for that, let me explain you one more slide so that you can answer that one. So the maximum value and minimum value, find the maximum and minimum value of the current. That is IL max and IL minimum if you want to find. So the IL max and IL minimum is, so the maximum current I max, IL max, the inductor maximum current is IL plus delta IL by 2. IL plus delta IL by 2. So the inductor minimum current is IL minus delta IL by 2. IL minus delta IL by 2. So from the IL waveform we can find. So this is how we will find the IL, I max and I minimum. Right? So if you know the inductor waveform, from that you can find the maximum value. IL will be the average value in between the waveform. So if you want to find the maximum value, it will be the IL plus delta IL by 2. IL minus delta IL by 2 is the I minimum. So now, by using this expression, I can find. So the peak value current in the switch. So the current, we need to find the peak value of the current. So now let us find the peak value of the current. So in the switch, we need to find the peak current. So which is equal to, the switch current equal to inductor maximum current. So inductor maximum current equal to IL plus delta IL by 2. IL plus delta IL by 2. So in case of buck converter, IL equal to I naught. IL equal to I naught. So if you find the delta IL, so you can find the answer. So now delta IC has given. Delta IC is given. So the peak to peak value of delta IC. So in delta IC equal to delta IL in case of the peak to peak value of the delta IC equal to delta IL in case of buck converter. In case of buck converter, if I draw the IC waveform, it should be like this. So which is equal to delta IL. The peak to peak value of the delta IC equal to delta IL. So delta IC already given, which is equal to 1.6. So it is given as 1.6. So we need to find the IL. So how can we find the IL? So 24 volts. So we need to find the IL waveform. So let us see that 1.6 delta IL by 2. Let me find the delta IL by 2. So I naught is also given, which is equal to 5 amperes. I naught is also given, which is 5 amperes. I naught, which is also given as 5 amperes. So IL equal to 5. Delta IL by 2. So 1.6 by 2. So which is equal to 5.8. Which is very easy. First read the data. Understand the concept. So you can find the answer. Now let us solve the next question. So here, so what they have given. So we need to find the average value of the source current, which is very easy. Find the average value of the source current. So which is equal to Vs into Is, that is input power equal to output power, V naught into I naught. So from this, if you need to find the Is value. So that is Vs is given as 12 into Is. So V naught equal to, it is a boost converter, right? It is a boost converter because the inductor is placed on the source side. So which is equal to 12 volts is given as V naught as Vs 12 by Vs divided by 1 minus D. So that is 1 minus D is the 1 minus 0.4. So it is equal to 1 minus 0.4. So which is equal to V naught 12 divided by 1 minus 0.4. So into I naught equal to 12 divided by V naught by R. That is 12 divided by 0.6 into R value is the 20. R value is the 20. Now, from this IS equal to 12 divided by 20 into 0.6. If you take the 20 into 0.6, it is 12. So it will get cancelled out and it is 1. And 12 by 0.6 and 12 will get cancelled out. So IS equal to 1 by 0.6, that is 10 by 6, 6 by 10, which is equal to 10 by 6, and which is equal to 5 by 3. So IS equal to 5 by 3. So now let us solve the next question. Let us solve the next one. Okay. Now let us find the input resistance. So how can we find the input resistance? So this concept is somewhat different. So try to learn the concept so you can find the input resistance very easily. So whatever may be the converter you can find. Let me explain you. So here any DC to DC converter, so we can represent as a transformer analogy. For example, so we can, the DC to DC converter is also called as DC transformer. DC transformer, right? So let us assume this ratio of, that is N1 by N2 is 1 is M is Pn, right? Let me write that. Let me write it as a 1 is M of D. So where M of D is the, it is different for the different converters. For example, it is buck converter. So it is buck converter. So M of D is the D. M of D we can take it as D. If it is boost converter, M of D we need to take it as a 1 by 1 minus D. 1 by 1 minus D. So here, if it is a buck boost converter, we need to take the M of D is the D by 1 minus D. Right? So now let us see how we can make this. So let it be the Vs and V naught. So now what is the, if it is considered as a DC transformer, so V naught by Vs equal to M of D. Right? So M of D. So where M of D can consider as, in this M of D can consider as, like in a transformer, we will take the K equal to N2 by N1. K equal to N2 by N1. In the similar manner, consider this M of D is a transformation ratio. So now V naught by Vs equal to M of D. So it is a buck converter, it is equal D. So that is V naught equal to Vs into D. So if it is a boost converter, V naught equal to Vs into 1 by 1 minus D. If it is a buck boost converter, so V naught by Vs equal to V naught by Vs equal to V naught equal to Vs into D by 1 minus D. For example, if I want to find the input resistance, how can I find the input resistance? So if I know the output resistance, R naught, so in a transformer, how can I find the input resistance in terms of output resistance? If the value is shifted from the secondary to the primary, so we can take it as a, so R input equal to R naught divided by K square. In the similar manner, the input resistance, R input resistance can be defined as output resistance divided by M of D whole square. You can take this as a shortcut so that you can directly answer the question. If you answer one question, it will be easy for you. Very simple. Like transformer analogy, so DC to DC converter is also called as DC transformer. So if I shift the output resistance to the input, so it has to be divided by the M of D whole square. So this M of D will be depends on the type of the converter. So but this formula is common for all the three converters. Now let us solve one question so that you can understand. So consider the boost converter. It is a boost converter. So what we need to find? In this case, we need to find the input resistance. So what is the output resistance they are given? 10 volts. So how can we find the input resistance? Simple, very simple. So the input resistance equal to, what is the formula? R0 divided by M of D whole square. What is the M of D? So because it is a boost converter, M of D equal to 1 by 1 minus. Let's find the M of D. So which is equal to 1 by 1 minus D whole square. So which is equal to 10 divided by M of D equal to 1 by 1 minus 0.6. 1 by 1 minus 0.6 whole square. 1 minus 0.6 whole square. 1 by 1 minus 0.6 is 1 minus 0.6 is 0.4. So 1 by 0.4 whole square. So if I take here, so it is in 10 into 0.16. So which is equal to 1.6. So the answer is 1.6 ohms. Our input is the 1.6. So it is the easiest method. Otherwise, you can do it by yourself also. Like Vs, the input resistance is equal to Vs by the conventional method. How can we do this? So here the input resistance is Vs by Is. Vs by Is. So how you need to find the Is? How you can find the Is? So which is equal to V0 into I0 divided by Vs. So if you find the Is and then if you substitute here, so you will get the input resistance. This is another method. But so directly you can apply this formula because we know the formulas of output voltage input voltage relation. From that you can easily find. So this is all about DC to DC converters operating in the continuous conduction mode. So almost the 80% of syllabus of the DC to DC converter is completed. If you can watch and complete this lecture, right? So thank you so much. Thanks for attending the session. I hope this was longest session till now, but this will be useful. This will be useful, and try to study like this. Try to learn like this. If you can find like this, if you can find the simplest way to solve the simplest way to understand the concepts, so you can easily complete the syllabus. You can easily complete the syllabus.